Hey everyone, welcome to Next Gen AI Academy. So in the last lecture, we discussed about the applications and the limitations of generative AI, and we know that these foundational models or large language models are very important in generative AI. So the today's lecture will predominantly be focused on to understand these large language models and the foundational architecture working behind it, right? So in the upcoming videos, you will be seeing that we will be talking about prompting and prompt engineering. We will also be talking about retrieval augment generation. We will be talking about LLMs and foundational model evaluations and their production reliability. So to understand all these videos, it's very important to understand the LLM foundation first, right? So let's get into it. First, let's discuss about what problem does an LLM solve, right? So what LLM is doing here, right? You might be wondering what large language model is doing here, right? So the major application of large language model is to predict the next token, right? Predict the next token, nothing else, right? So let me open ChatGPT and will show you one example, right? So here, if I ask capital of India is, just I hit the enter. Let's see the output. The capital of India is New Delhi, right? So the output is New Delhi. So how it give me an answer of New Delhi, right? I'll just talk about it, right? So since LLMs are predicting the next token, right? Predicting the next token, right? So there must be a lot of tokens. Let's say token 1, token 2, and token 3. Token 1 is assigned to, let's say, Mumbai, right? Token 2 may be assigned to New Delhi, right? And token 3 is assigned to, let's say, Jaipur, right? And the output probability of Mumbai may be, let's say, X, and probability of New Delhi is, let's say, Y, and Jaipur is, let's say, Z. Here the ChatGPT gave New Delhi because the Y was greater than X and Y was greater than Z, right? So that probability comes from the learnings, right, of an LLM. So we will be discussing about how the large language model works, how the training works, right, and how the weights updates on top of it, right? So we will be learning in the next slides. But here the basic work of an LLM is to predict the next token, right? And these tokens are trained on these LLMs in such a way that the LLM is able to predict the next tokens, right? So tokens, we will be talking about the tokens as well in the next slides. But here the predominant thing which I want to let you all know that what is the application of LLM is to predict the next token. It's not learning like a human mind. It's not learning like other ML and DL approaches works. It's learning by just understanding the token and predicting the next token, right? Correct. So let me talk about what are the tokens, right? What are these tokens, right? You all must be wondering about what are the tokens if you're coming from previous DL or NLP experience. You might have heard about token, but if you don't know what tokens is, let me explain, right? So uh, let me give you a simple query called my name is Ram. So this is a simple prompt I'm giving to my large language model, let's say, right? So since the machine learning models or deep learning models or these large language models doesn't understand text, right? So it's very important that we assign some values to these text, right? So let's say I assign these value to 0, these value to 1, this to 2, and this to 3, right? So whenever my model will get 0 as a retrieval, it will understand the 0 means my, right? So that's how we are assigning these numbers to these texts, and these numbers are nothing but tokens, right? And these tokens also furtherly compute as embeddings, right? Embeddings are nothing but vectors or vectors in multi-dimensional space, right? So how these texts becomes numbers? So I think it's clear now that the model assigns some random values to these texts, right? And these texts are furtherly used to train these models, right? I'll explain how the training works of these large language models, but here my sole focus here is to make you understand what tokens are, right? So tokens are nothing but the mathematical numbers or mathematical vectors, mathematical representation of text, right? Of text, txt, right? So I hope it's clear. And this calculation internally done, the weight updates done, and then the model is able to generate the output in terms of the next predicted token, right? Next predicted token, right? So you might be wondering that, okay, so I do understand that whatever text data you're giving to the model is perceiving this data as tokens, but internally how it reads the text or reads the tokens, and what sort of architecture does it use, right? So internally it uses transformers architecture, which are attention based architecture, right? Attention based architecture, right? So you might have went through DL based principles, right? DL based foundational principles, right? Where they build first RNNs, right? They build GRU, and on top of it uh, they make sure that the sequential learning happens here, right? Sequential learnings. What sequential learning is? So model were able to understand single word, let's say cat. So model was able to understand this before cat, right? But in RNNs, which are recurrent neural networks or GRUs, if I give this is a cat, right? So the model was able to sequentially learn this, then is, then a, then cat in form of tokens, right? So model was able to understand. But if I say that this is a cat, right? Its color is white, right? So the model, the RNNs and GRU architectures were able to understand what this is a cat is. But when I tell it's, now these architecture fails to understand that what it's referred to here, because there was no attention given to these tokens or these embeddings, right? And that's how the transformer came into picture, right? If you already aware about transformer based architecture, it's well and good. If you don't know, i'll I'll add the link of the attention is all you need research paper, and I'll highly recommend you will go through and read this research paper, right? It's very informative, and you will be able to understand the entire encoder decoder based architecture of these transformers, right? So when transformers came into picture, they were not just inheriting the sequential based learnings, they were also giving attention to these words. So model can understand what the text is talking about, right? So every token was also learning that how the other tokens are related to it, right? So in this case, this is a cat, its color is white, right? So now this its token understand that now it refers to only the cat only, right? So the tokens are internally relating to each other via giving some attention to it, right, at the same time. That's why we are using transformer based architectures, and these are better than the previous architectures we have used. It might be RNN based architecture, GRU based architecture, or any other form of architectures, right? So the transformer based architectures are highly recommended when it comes to Gen AI use cases or building large language models which can understand the text, right? So I hope it's clear how the transformers are, and why these are being used uh, while creating these LLMs, and why these are the basic architectures which being used in most of the large language models uh, which are being used in the industry right now, like ChatGPT, Claude, uh, Gemini, etc. Right? So I hope it's clear. And if you want to understand the mathematical intuition behind it, I will highly recommend it. I'll highly recommend you'll go through the research paper I'll attach with the video itself, right? Uh so yeah, now let's talk about how LLMs are trained, right? So the training source can be anything, right? Can be. So as we all know, the definitions of large language models is nothing but the the basic architectures related to transformers which are being trained on large text data, right? So the training source here can be a book PDF, right, or any other file, not just PDF, any other file, right? Blog, right? Conversations, right? Like we can use some audio files, right? Audio files from maybe Spotify audio files, Spotify or any other podcasting platform, right? Maybe we can get some YouTube files as well, right? In terms of audio, and use it as a text to train these models, right? So the idea here is how we will be able to train these large language models. The source can be anything. It's just that how you format the data and give it in the similar output, right? So yeah, the data preparation might be tricky for these training, but the source can be anything, right? Might be a blog, might be a conversation, might be a book, might be a research paper, anything, right? So the fundamental training loop would look like this. Training loop, right? So first you give the text, right? It will predict token, right? Right? Assign some probability to it, right? Probability, or you can say score, right? Basis score, the weights will update, right? Right? Weights will update, and again it will predict the next word. So millions of time, thousands of time, this happens again and again, and the weights are updating to make sure that we are approaching to the point where the accuracy is maximum, right? Accuracy of the model is maximum, right? So I hope it's clear now how the training loop is working here. We are just giving text data to these models. These models are predicting something in the first iteration or maybe in the first epoch, right? While getting the output, we'll sample it, get the scores, right? And we'll again update the weights accordingly basis the error will be getting, right? So error is nothing but error is your uh, y predicted minus y true, right? So this is how we will be calculating uh, internally we will be calculating the error, right? And basis error will again update the weights, and the loop will work simultaneously to make sure that we'll achieve a point where our accuracy will be maximum, right? So now let's talk about how large language models hallucinates even if trained on very large text data, right? So let's say sometime the context is missing, right? Or let's say limiting context, or let's say no training, no training happen, right? So let's say you trained a large language model, you train a large language models on, let's say you trained on C++ in syntax, right? And your LLM is now able to generate code, right? it's it's able to generate code in C++ now, right? But if you'll ask the similar LLM to generate code in Scala, now since the context is not there for Scala, the LLM has never seen or never executed the tokens related to Scala syntax. Now the LLM will just predict, right? It will just will give an output basis it's the training happened on these LLMs, right? So the LLM might confidently give you the wrong answer, right? It might again give you the C++ code instead of Scala, right? Instead of Scala, right? So this is the case of hallucination. So the example is not important. The important thing here is to understand why LLM hallucinates, right? LLM hallucinates when the context is missing, or maybe the limited context is there for model training, or there's no training happen on the query which we are retrieving the information on, right? So it's very important to understand you cannot expect LLM to be 100% true even though the training is it was not part of the training, right? So yeah, this is the case of hallucination where the LLM doesn't have context or maybe have limited context, and you are going deeper into the query and you want to get the expected results, right? So this might be a case of hallucination at the same time because the model know nothing about the query you are putting into it, right? So yeah, that's for it today. In the next lectures we'll be discussing about prompting, RAG, and many more, right? Have a good day. Bye.